Hi, and welcome to Fluid Dynamics 2. This lesson, I was just going to look at Bernoulli's equation done two different ways. Talk about it a little bit, but what we're getting into here is lots of maths, and lots of maths, if I'm completely honest, I'm not great at. This is engineering, which, as we all know, is not my strong suit. But hopefully just by looking at these we can explore some of the ideas around Bernoulli's equation. So this is a simplified form. It says P plus half, this is a rho, that's not clear, rho speed squared equals P0. So what's that? Well, this is the static pressure. So this is what we were talking about last lesson. It's the pressure on something inside the liquid, plus the dynamic pressure. This is the extra pressure you get from moving. Okay, so as something's moving, it's just going to be applying more force. So remember, this is all just measured in pascals, just force per unit area. So as you're moving, providing more force. You can also, interestingly, define this as the kinetic energy per unit volume, which turns out to have the same units. You can do fundamental unit analysis on that in your own time, which is another interesting way of thinking about it. So just as there's more kinetic energy in each bit of the fluid, the dynamic pressure will go up, equals the total pressure, which isn't especially interesting. It's just a pressure plus pressure equals a pressure. But it's just a way of working that out. A more exciting look at Bernoulli's equation goes like this. I really like this one. The speed squared divided by 2, add g times z plus p divided by rho equals k. Let's go through that. So v we already know is just the speed. G is just gravity, it's gravitational field constant, multiplied, and I really like this, z represents the elevation that you're talking about. Okay? So obviously the higher up a liquid goes, that's going to change things. So as it moves from elevation to elevation, that's going to be something that very often, think about water flowing down a hill, is going to be what gives you the energy to make all the other things work. It's defined as z, by the way, because of x, y, z coordinates. So, and this is normally how it's done in physics, with x being along, y being across, and z being the up-down one. Okay. Also, watch out on your degrees. Sometimes they define it as ijk rather than x, y, z, something that tripped me up a lot when I was starting, so just watch out for that one. So z is our elevation. P, that's just pressure, that's easy. Rho is a thing called viscosity, or the density of the fluid, I guess, probably a more accurate way of describing it. So that's just density, kilograms per metre cubed, how heavy the fluid is. And K is just a constant. So if you add up the speed squared divided by 2, the gravitational field times the elevation, and the pressure divided by the density, that will be a constant, which is useful because it means that if you increase the elevation, you know you're going to have to decrease one of these. If you increase the speed, you'll have to decrease one of these. And this form of Bernoulli's equation is far more useful. The elevation element, by the way, is something that actually makes almost all plumbing work to this day. If you think about it carefully, all the reservoirs that supply us are above us, always up in the hills. And the reason that's simple, because we want the water to flow down to us. We don't want to put extra energy pumping the water. We want the sun to do that. The sun's energy evaporate the water, drop it above us, and then flow down. So elevation actually turns out to be an incredibly important idea within all plumbing, all fluid dynamics. There's some really neat things you can do with elevation. If you go to Chatsworth House, one of the big stately homes outside of Manchester, they actually, way back in sort of the 1800s, made a fountain that could shoot 30 feet in the air by running a river off the hill behind them. So because it was dropping by such a great distance, it was able to shoot up a fountain with nothing that we'd consider mechanical involved in that. That was just messing with this elevation idea. In Australia right now, they're doing something really mad, which is there's a lake on a plateau. It's about 200 metres up on top of solid rock. And what they're doing is they're digging a borehole from the cliff all the way up through to the lake. It's one of the biggest engineering projects the world has ever seen. Because what you'll then have is a steady flow of water dropping through a massive distance, and they're going to use that to run a hydroelectric power plant. So you can do all sorts of things by messing with this elevation idea. It's a very important idea within fluid dynamics in general. So not going too deep on the maths here, because honestly the more interesting equations just devolve into very difficult calculus, but just hopefully showing you some of the underlying principles so that your brain can start to tune into them, and when you go to university in September you've already seen them. Okay, enjoy your weekend.